Welcome back to Chemistry 4300. In this video, we're going to finish up Chapter 3 on the kinetic theory of gases. Now, we've already learned all about the kinetic theory of gases from Bernoulli to Maxwell. And one of the things we need to do is to see if Maxwell's molecular speed distribution is actually correct. So we want to do experimental verification of this. And it turns out that this was done back in 1955, much later than when Maxwell did his derivation. But it was about that time that we could get the first real definitive experimental results. So let's take a look at this experiment by Miller and Cush. So what they did is sort of described in this picture here, and this is going to take some explaining here. So this is a cutaway view of a chamber that's connected to a pump. So it's going to be pumped out so that there's a vacuum in here, as close as possible to a vacuum. And inside this chamber, on one side, there'll be an oven, and in that oven, there's going to be potassium or thallium metal, one of the two. And they're going to be heated up so that they're above their melting point, so that they're now in the vaporization point, then they're going to be vaporized so that they're in the gas phase here. And at some fixed temperature, there should be a Maxwell distribution of speeds. We want to detect what that distribution of speeds are inside the oven. Now, this oven has a slit here, so as the molecules, or in this case, the atoms, are flying around inside this oven, some of them will escape out this slit and go straight across this chamber to where there's a detector. And this detector is going to detect the count, or the number of thallium or potassium atoms that hit it. This is a type of surface ionization detector that will give us a count. So there is a clear path from the oven across the chamber to the detector. Now, in this drawing, there's a big cylinder that's placed in between. That's a barrier to prevent any of these atoms from flying across this straight path here. But what's interesting about this cylinder is that they've cut a groove into the cylinder. Now, the cylinder is not on the axis of the beam. The cylinder is off the axis of the beam. The beam is actually passing would pass through the cylinder on the outer edge of the cylinder. So it's just enough that the cylinder is blocking the beam, but just barely so. And then on the cylinder, they've cut a groove so that there's a way for the gas molecules to pass across the surfaces of the cylinder, but only in a very particular way. So what's going to happen is that the gas molecules can only follow this path. So as this cylinder is rotated, so there's an angular frequency here. The cylinder is rotated, and this groove here is at an angle phi, at an angle, it's not cut directly across, but it's cut at an angle phi across the surface. So as this cylinder is rotated, some of the atoms will pass through, and some of them will hit the groove initially. And when they hit the groove, if the cylinder is moving too slowly, then they will just smack into the top of the groove and they'll be stopped. If the cylinder is moving too quickly, then they will be smacked up by the bottom of the groove and they'll be stopped. But what's happened is if the cylinder is moving just right, then an atom that's coming out will enter the groove, and it's going to continue along this trajectory here. But what's going to happen is that the groove is going to move up as the cylinder turns, and the molecule is going to stay in a region of the groove because the cylinder is going to be rotating in such a way that certain molecules with a certain speed will manage to navigate all the way across, because that groove will be in the right place at the right time so that they can continue along that trajectory. I know that seems crazy. You can imagine if you were flying a spaceship and you were or more like a rocket. If you were shooting a rocket out of this side to go over here, you want to time the rocket so that as the rocket comes out and this wheel and this cylinder turns, that you hit the groove and you pass all the way through with this groove sort of always aligning with your path as you move across. So this is the experiment. Think about it for a while, but what you can work out is that for a fixed rotation speed, only molecules in a very small range of speeds can travel from the furnace to the detector. And you can calculate what that speed is, because it's going to be equal to the angular velocity of the cylinder times the length of the cylinder divided by this angle of the groove, which is phi. So if you vary the speed of the cylinder moving, then you can vary the range of speeds that can make it through this apparatus. Okay, so that's how their experiment works. And so what they're going to do is they're going to measure the count here, this, excuse me, the count at this detector as a function of the speed, and then convert that into the velocities that are making it through, and then have a count as a function of molecular speed. Okay, so let's take a look at the experimental results. So this is the result for potassium and thallium vapor. Now what they've done is they've calculated the speeds, and then they've scaled the speeds by the mode of the distribution. So remember, the mode of the distribution is 2 kBt over m square root. So that means that 1 here corresponds to what should be the mode of the distribution. And so the green line here is the theoretical prediction from Maxwell's distribution for speeds. And the dots here that plotted are the different runs for potassium vapor, and you can see it beautifully lines up with the predicted value for Maxwell's distribution. Over here on the same, you see here's the thallium vapor, so a different mass. So again, it's all scaled so that 1 corresponds to the mode here, and here you see the experimental data sort of beautifully matches there. So it's really, I think, it's from 1955, it took many years, 100 years to do this, but the experimental verification is really impressive. Here's some results tabulated here for the different runs in potassium or thallium. So from the oven, they knew the temperature of the oven, they could calculate the velocity. So from the oven temperature, they could calculate the velocity max, and so these are the maximum velocities for these cases, and then these are the predicted ones from, I'm sorry, this is from the oven temperature, and this is what they measured. So this is predicted from the theory, and this is what they measured experimentally. And so similarly here for the thallium, and here's from the experiment. Okay, so that I think is it. And then the last thing I want to do to finish up this chapter is to give you one last assignment. We didn't talk about the distribution of kinetic energies, but that's something I want you to do on your own. So start with the speed distribution and derive for yourself the distribution of kinetic energies, and you should be able to come up with this expression. This is what a plot of them look like. So this is the distribution of kinetic energies that you get from Maxwell's equations, and here are the distributions for, this is actually for nitrogen, this is for 100, 300, and 1,000 Kelvin. Okay, that's it for this video, and that's the end of chapter 3.